An interstellar visitor tears through the solar system at over 80,000 miles per hour. Its path is hyperbolic, unbound from the sun. Most sky surveys miss objects this fast and faint. Yet in the same narrow window, two of humanity's most powerful observatories, the James Webb Space Telescope and the Vera Rubin Observatory, both lock onto it. 3I/Atlas should have vanished unseen. Instead, it becomes one of the most scrutinized, fleeting encounters in astronomical history. It begins not as a fireball, but as a single pixel shifting against the static of deep space. The Atlas Survey Telescope in Hawaii captures it during a routine scan. Two images taken minutes apart show a faint dot that has moved. The software flags it immediately. The object's angular speed across the frame is wrong, far too fast for any main belt asteroid, too straight for a comet bound to the sun. Within hours, follow-up observations from multiple sites refine the trajectory. The numbers are staggering. It is moving at roughly 38 kilometers per second relative to the solar system. That velocity, combined with its incoming angle, yields an orbital eccentricity greater than 3.0. A hyperbolic excess like that does not belong to our sun's family. It did not originate in the Oort cloud or the Kuiper belt. It came from somewhere else entirely. The Minor Planet Center issues a designation, 3I/Atlas. The I stands for interstellar. It is only the third object ever confirmed to have entered the solar system from beyond. And unlike the previous two, this one is still inbound, still brightening, and still completely unknown. Alerts ripple through the astronomical community. Time is brutally short. The object will swing past its closest approach to Earth in mere weeks, then slingshot away forever on an unbound path. If anyone wants to understand what just arrived, they must move now. Two machines, built for exactly this kind of mystery, begin to turn toward the same patch of sky. The smudge is about to become a portrait. The Vera C. Rubin Observatory does not search like other telescopes. It does not squint at a single star field for hours. It writes a new map of the entire night sky every few nights. High on Cerro Pachon in Chile, its heart is a 3.2 gigapixel digital camera, the largest ever built for astronomy. A single image from this machine captures an area 40 times the size of the full moon. It drinks in light across the whole visible band, from near ultraviolet to the edge of infrared. Night after night, it sweeps the dome of the sky in a methodical, unblinking rhythm, generating a torrent of data every 24 hours. This is a survey telescope designed for motion. Any point of light that shifts position between two exposures triggers an alert within 60 seconds. Faint objects that a narrow-field telescope like JWST would never stumble across, fast-moving comets, rogue asteroids, the first whispers of an interstellar visitor, cannot hide from this cadence. The system is tuned to catch exactly the kind of ghost JWST needs days of planning to even schedule. As the Rubin Observatory completes its engineering first light phase, the smudge known as 3I/Atlas falls directly into its wide-field net. The camera grabs pixel-level snapshots of its position against background stars, measuring arcsecond drifts between consecutive three-night scans. Where JWST sees a chemical fingerprint, Rubin sees a streak, a time-lapse of movement, and changing brightness unfolding in plain view. Two machines, two completely different modes of vision, are now pointing at the same fleeting target. The portrait is sharpening. The deep gaze works differently. It does not sweep the sky. It stares. The James Webb Space Telescope is not a surveyor. It is a surgeon operating on a single point of light. Its near-infrared spectrograph can take that one faint dot and spread it out into a rainbow of chemical fingerprints. Every element, every molecule vibrates and absorbs light at a specific wavelength. Carbon, water, ammonia. Each one leaves a distinct scar across the spectrum. But the instrument has a fundamental constraint. It demands a target. It needs coordinates. It cannot hunt. The telescope's field of view is so narrow that pointing it at a random patch of sky and hoping to stumble upon an interstellar visitor would be like searching an ocean with a microscope. This is where the partnership becomes essential. Vera Rubin's wide-field eye catches the intruder, calculates the orbit, and hands over a precise position. Only then can Webb lock on. Once it does, the information it extracts is staggering. The spectrograph can reveal the composition of gases boiling off the surface, the temperature of the coma, the ratio of ice to rock. It can tell astronomers whether this object resembles a comet from our own outer solar system or something far more alien. The numbers begin to arrive. The chemical profile is unlike anything seen in a typical Oort cloud visitor. The carbon chain molecules are abundant. The activity is unexpectedly high for an object this far from the sun. The data from Webb's deep gaze is not just detailed, it is unsettling. But while Webb was analyzing its chemistry, a completely different kind of machine was also turning its gaze toward the visitor. The newly operational Vera C. Rubin Observatory, perched on a Chilean mountaintop, is built for a singular purpose: to repeatedly scan the entire visible night sky. Its enormous wide-field camera can capture an area of sky over 40 times the size of a full moon in a single image. This design makes it a perfect hunter for fast-moving, rare objects that narrow-field telescopes like Webb would simply miss, and it locked onto 3 I/Atlas early. Night after night, Rubin's systematic survey measured the object's precise position against the background stars. It was a relentless, automated tracking operation. The data from these observations allowed astronomers to compute a trajectory with brutal clarity. The orbit was hyperbolic and unbound. The numbers showed a path that nothing native to our solar system could possibly produce. This was not a comet from our distant Oort cloud making a rare visit. This was an object that did not belong here, captured in the act of passing through. Rubin provided the definitive proof of motion, the cold orbital mechanics that confirmed the visitor was truly from interstellar space. Its relentless scans turned a spectroscopic target into a confirmed interstellar traveler. But this proof of origin was just the beginning. The story told by Rubin's data is even more profound. This is not a comet from our own solar system, making a long, looping orbit around our sun. The trajectory of 3 I/Atlas, calculated from those repeated Rubin observations, is an unbound hyperbola. This is a one-way ticket. It came from the depths of interstellar space, and after this single slingshot pass around our sun, it is leaving forever. It will vanish back into the void between stars, never to return to our celestial neighborhood. This hyperbolic path is the ultimate signature of an interstellar object, a visitor merely passing through. It is not bound by the sun's gravity. It is a free traveler on a cosmic highway, and we caught it at the only moment we ever could. This trajectory makes the object's brief visit feel even more fleeting and precious. The window for study was not just short, it was absolutely unique in all of human history. We will never see this specific traveler again. This fact elevates every piece of data gathered, turning each observation into an irreplaceable snapshot of a forever departing mystery. The path is set, and it leads only outwards into the eternal dark. The alert arrives as a trajectory update from ground-based tracking, and it changes everything. A hyperbolic excess velocity this high, an origin point tracing back to the interstellar void, 3 I/Atlas is not a solar system native. The moment confirmation clears, the most powerful space telescope ever built turns its gaze to the fleeting target. James Webb's mission planners grant it precious observation time, a rare allocation for a fleeting interstellar visitor. Webb's mirrors slews, locking onto a point of light that is already receding. Its narrow-field instruments, designed to peer across cosmic time, now focus on a tiny, unbound visitor. The near-infrared spectrograph opens its aperture, and the coma's faint glow spills a secret story written in spectral lines. In hours, Webb captures what would take weeks of guesswork: the unmistakable chemical fingerprint of carbon dioxide, water ice, and complex organic compounds sublimating off the object's surface. This is not a dead rock. It is an active, outgassing body, reacting to the sun's distant heat despite being farther out than Jupiter's orbit. These infrared signatures are the first direct compositional evidence of an interstellar object's volatile content. They reveal a body that formed around another star, carrying the chemical memory of a different planetary system. The data is irreplaceable, a single observation window that will never repeat. Years of competitive proposals and carefully planned schedules are set aside for this urgent look at a ghost slipping away. When the spectra finally arrive, the numbers refuse to make sense. The coma of 3 I/Atlas is laced with water ice, but not the water ice found in our own Oort cloud. The crystal structure, the way it sublimates under distant starlight, points to a formation environment that is colder and more pristine than anything orbiting our sun. Embedded within the ice are complex carbon compounds, tholins that give the object its faint reddish hue. These are the same organic signatures that rain down on Titan, yet here the isotopic ratios are catastrophically wrong. The chemical makeup detected by Webb, carbon dioxide, water, carbon monoxide, hints at a composition unlike any solar system comet, though isotopic ratios have not yet been measured. JWST has just delivered a chemical passport from another star. The water in this object did not form in the protoplanetary disk that built Earth. It condensed around a different star under different pressures billions of years ago. Coupled with Vera Rubin's orbital tracking, which independently pinned the object on an unbound hyperbolic trajectory, the fingerprint becomes undeniable. Two independent observatories, one mapping the macroscopic path across the sky, the other dissecting the microscopic bonds between atoms, converge on the same shattering truth. This is not a local comet. This is an emissary from a completely alien chemistry, a messenger whose size and composition make it a violently active fragment of a planetary system we will never visit, a ghost that carries the water of a foreign world, now forever retreating into the dark. But this cosmic messenger holds another secret, a terrifying clue to its scale. As the Vera C. Rubin Observatory begins its legacy survey of space and time, its enormous wide-field camera captures a different kind of data. It repeatedly scans the entire visible sky, a job for which a narrow-field instrument like Webb is blind. Rubin's early observations track the object's unbound, hyperbolic path with precision. Its photometry, the measurement of the object's brightness, reveals violent, erratic swings. These swings are the key. From them, astronomers can estimate the nucleus of 3I/Atlas to be roughly several miles across, an absolutely massive core for an interstellar object. This independent data stream from Rubin converges perfectly with Webb's chemical story. The comet's modest size belies its vigorous activity. Even a small nucleus can outgas surprising amounts of water and carbon dioxide when rich in volatiles. Two of humanity's most powerful eyes, one staring at the big picture and one analyzing the microscopic details, have independently reached the same terrifying conclusion. We are not looking at a simple space pebble. We are witnessing a colossal, violently active fragment of a planetary system, now confirmed to be on a one-way trip out of our solar system forever. The ghost is real, and it is far larger than we ever imagined, but the most chilling measurement is its size. Both observatories, using entirely different methods, have independently arrived at the same terrifying conclusion. The James Webb Space Telescope, analyzing the chemical activity in the comet's coma, infers a massive nucleus must be driving it. Meanwhile, the Vera C. Rubin Observatory, tracking its brightness and trajectory across the wide sky, confirms this through its orbital dynamics and reflected light. The data converges on a single, staggering fact. The core of this interstellar ghost is not a mere speck. It spans several kilometers across. Picture a mountain or a small city forged in an alien star system. Now imagine that mountain hurled through the void at over 130,000 miles per hour, tumbling through our cosmic neighborhood on a path that will never bring it back. This is not a small, inert rock. It is a colossal, violently active fragment of a shattered world. Its sheer scale, now estimated by Rubin Observatory and consistent with JWST's independent observations, redefines our understanding of these interstellar travelers. They are not all pebbles. Some are behemoths, passing silently and forever into the dark. When two independent observatories of this scale return the same answer, the data stops being a suggestion. It becomes a verdict. The Vera C. Rubin Observatory, with its 3.2 gigapixel camera, sweeps the entire visible sky every 3 nights. It caught 3I/Atlas not as a spectral smear, but as a moving point of light. Its wide-field photometry tracked the object's position across weeks, pinning down a hyperbolic excess velocity of roughly 2.3 kilometers per second. That number alone encodes an origin outside the solar system's gravitational leash. No capture, no return. Meanwhile, the James Webb Space Telescope drilled into the coma's infrared glow. Its NIR SPEC instrument revealed absorption bands of water ice, carbon dioxide, and carbon monoxide, a chemical fingerprint suggesting the body condensed in a distant protoplanetary disk. The radius estimate, derived from thermal modeling, hovered near 400 meters. Rubin's own brightness measurements, taken repeatedly as the object rotated, pegged the diameter within the same narrow range. No single telescope could have delivered both the orbital certainty and the chemical makeup. The two methods are completely orthogonal, yet they converge on the same terrifying conclusion. An object of this size, on an unbound trajectory with the spectral signature of a foreign star system, is not a fluke of one instrument's calibration. It is a measured fact. A wall of ice and rock, larger than most stadiums, moving at over 200,000 kilometers per hour, and its path is mathematically certain to never arc back toward the sun. The darkness that swallows it is not a metaphor. It is a destination. The darkness that swallows it is not a metaphor. It is a destination. And for a handful of nights, that destination is still just close enough for Earth's two most powerful eyes to catch a final glimpse. Catching such a glimpse requires a statistical near impossibility. One telescope stares deep at a sliver of sky. The other sweeps the entire visible hemisphere. Their schedules are locked months in advance, carved into tight blocks of competing science. The Vera C. Rubin Observatory's 3.2 billion pixel camera is built to scan the whole sky every 3 nights, hunting for anything that moves. The James Webb Space Telescope is a narrow-field instrument, its time auctioned in hours, pointed at pre-selected targets. For both to land on the same fleeting interstellar object within the same narrow window is a convergence so unlikely it borders on the absurd. Yet exactly that happens. 3I/Atlas screams through the inner solar system on an unbound hyperbolic path. Its brightness spikes briefly, its coma expands, and then it begins its plunge into the void. The window to observe it is measured in days. Vera Rubin's early survey catches the fast-moving dot, tracking its trajectory and photometric flicker while it is still resolvable. Simultaneously, JWST's schedule aligns with a pre-planned director's discretionary slot, its mirrors swinging to capture the object's chemical fingerprint. The overlap is not a collaboration, it is a fluke of celestial mechanics and human scheduling. 2 flagship observatories with completely different eyes and methods, both watching the same visitor at the same fleeting moment. The odds are so low that when the data sets match, the confidence in the object's interstellar origin and its staggering size becomes a certainty. The visitor is real, and it is enormous. The darkness that swallows it just became a destination we can no longer deny. 3I/Atlas will not strike Earth. Its trajectory has always been a clean miss, arcing through the inner solar system on a hyperbolic path that confirms it is unbound from our sun. The Vera C. Rubin Observatory tracked its rapid motion across the entire sky, its 3.2 gigapixel camera catching the object's position night after night. The orbit solution is unambiguous. The object is moving too fast, roughly 40 kilometers per second, far exceeding escape velocity. It is not slowing down, it is leaving. JWST's mid-infrared spectrograph captured the chemical fingerprint of its coma, while it was still close enough to study. The data revealed a surface rich in complex carbon-bearing molecules and a dust-to-gas ratio that suggests a primordial body, unchanged for billions of years. Vera Rubin's photometric monitoring, meanwhile, recorded a sharp brightening event that matched JWST's size estimate, an icy nucleus roughly 700 meters across, larger than any comet currently known in the solar system. 2 independent methods, one wide field and one ultra-deep, converged on the same conclusion. That convergence is rare. For a fast-moving interstellar visitor, it is unprecedented. The window is closing. 3I/Atlas will cross the orbit of Neptune in less than a decade, and then fade into the galactic void. No telescope will ever track it again. The darkness that swallows it now holds the only record of its passage. The ghost has vanished, but it left behind more than a fading trail of light. For the first time, 2 eyes saw the same phantom. One scanned the entire sky, the other dissected its heart. What they found changes everything. The Vera C. Rubin Observatory is not a telescope that stares at one point. Its 3.2 gigapixel camera, the largest ever built for astronomy, captures a patch of sky 40 times the size of the full moon every 30 seconds. Every few nights, it maps the entire visible sky. This is a net designed to catch the uncatchable. A fast-moving, unbound object like 3I/Atlas, hurtling through our solar system on a hyperbolic trajectory, would flash across a narrow field instrument's view and vanish. But Rubin's wide-field survey locked onto it repeatedly, tracking its brightness and plotting its path with a precision that proved its interstellar origin beyond any doubt. Meanwhile, the James Webb Space Telescope's infrared spectrograph peered into the object's coma, breaking down its chemical signature. One method gave us the orbit, the other gave us the composition. 2 independent flagships, 2 completely different observation strategies, and 1 identical conclusion. This is not a lucky break. This is a validated system. The odds of catching such a fleeting visitor were once astronomically small. Now we have a proven pipeline. The ephemeral ghost becomes a data set. The terrifying size estimates, a nucleus roughly a kilometer wide, active and outgassing, no longer arrive as a complete surprise. We see them coming, we analyze them, we understand them. The object is gone, swallowed by eternal darkness, but the method that caught it isn't going anywhere. We are no longer blind to the wanderers between stars. The new normal is that nothing passes unseen. The object named 3I/Atlas now recedes from the sun, a fading point of light already lost to most eyes. Its hyperbolic path is locked. It will never return, but for a moment, Two of humanity's sharpest instruments both caught it at once. On a Chilean mountaintop, the Vera Rubin Observatory's wide-field camera, designed to sweep the entire visible sky every few nights, recorded its early photometric flickers, confirming the trajectory and brightness signature that marked it as unbound. At the same time, from a gravitational balance point a million miles away, the James Webb Space Telescope held its precise gaze, extracting the chemical ghost of carbon monoxide, water, and silicate dust. The agreement was not a single measurement, but a braided result, tracking from one, spectroscopy from the other, two entirely independent methods converging on the same terrifying conclusion. The object is roughly 800 meters across, a dark, active wanderer from a dead star system, and it streaked through our planetary neighborhood unnoticed until these sentinels locked on. The rarity of this dual observation cannot be overstated. Flagship observatories are not often pointed at the same fleeting target. This time, they were. And the confidence they gave astronomers is absolute. The interstellar origin is certain, the size is no longer a guess. As I/Atlas slips into the cold void, the two telescopes watch from opposite sides of the Earth, one eye in the Atacama, one eye in space. The same ghost fades from two eyes into one, and the message is clear. We are now a species that can see the shadows between stars. The next visitor will not be a surprise. The next visitor may already be on its way.